All right, cool. Thank you all for joining us today. My name is Ashley, and this is AG up front. We're both software engineers on the gRPC library maintainers team, and we also both work on the broader networking stack for Google Cloud. So thank you all for joining us here for the last stretch of the day. So today we'll be giving an iceberg-style tour of how we think about performance in gRPC from the maintainer's perspective, starting with some broad principles of performance analysis, and then diving deeper into the tests and tools that we use to analyze the performance of the gRPC libraries. Finally, we'll come back up to the surface and give you all a sneak preview of some of the cool features and improvements coming soon. So let's start at the top. Why do we care about performance? Well, quick show of hands. How many of you want your service to handle more requests and faster and for the same amount of compute? Yes, cool. How many of you want your service to use less resources so it doesn't rack up a huge bill from your favorite cloud provider? Yeah, I think we all would like to save money. So the goal of performance optimization is pretty simple. We want to do more useful stuff and for less cost. And actually earlier today, Gina and Arvind from the gRPC maintainers team talked about how you can do just that with proxyless service mesh and gRPC. But in general, the problem of actually measuring and improving the performance of a service is very complex because there are a lot of critical factors that are unique to a particular service. So the way that one service owner thinks about performance is going to be very different from the way another service owner would, because their needs and their resource constraints and their ecosystems are going to be different from each other. In general, though, there are a few common themes that we can use when approaching the problem of how to analyze performance for any given service. So first of all, the why. Why do we want to measure performance? So this goes beyond just improving how much useful work it does or reducing its cost. The reason why continuous benchmarking and profiling of our service is useful is so that we can build a holistic view of how all the components and dependencies in our service interact with each other and how those interactions evolve over time. When we look at many different points across the service, we can identify exactly where the critical paths are and use that to make informed decisions on what sorts of optimizations are most helpful for us. And by gathering performance data over time, we can gain a better understanding of not just the baseline performance trend of our service, but also predict how its behavior might change in response to some new changes we introduce and what the potential magnitude of the impact could be. So now that we've convinced ourselves that we should measure performance for our service, how should we actually do that? So whatever it is that we care about measuring, it's critical that the staging environment where we're analyzing our service's performance is as similar to the production environment as possible. The more comprehensive our benchmark coverage, the better signal it'll give us on how our whole service is going to behave in reality. The problem here is that the more realistic the benchmark is, the more expensive it'll be to run. And it might not always be feasible to simulate a workload at the same scale as what you actually see in production. The catch here is that your service might behave differently when you give it different workloads. For example, under staging workload, your service might appear to be input bound, whereas in production, it might actually be compute bound. And the way to address those two problems are going to be different from each other. So it's very important that we apply the solution to our service that actually improves things in reality. So far we've touched a bit on why and how we should measure performance for any given service. But from the gRPC maintainer's point of view, we're in a slightly different position from y'all in that we don't build or run services ourselves. Rather, gRPC is used by other developers, such as yourselves, to build your microservices. So this means that there are basically an endless number of different service architectures out there that involve gRPC, and each of them is going to have their own unique needs and goals and constraints and environments that they need to work with, which will impact their performance trends in unique ways. So because of that, from the library maintainer's point of view, we can't really provide a definitive answer on how you should optimize your service, because that depends a lot on your particular situation. Instead, what we focus on as maintainers is we strive to build an RPC library that's both feature-rich and performant for as many of those use cases out there as possible. We know that you rely on gRPC to power the critical paths of your applications, so we invest considerably into testing and improving the library's performance so that you can rest assured that gRPC is delivering the performance you expect. So to achieve all that, we maintainers focus on a few driving principles. First of all, We want to build a feature-rich library while minimizing the overall performance impact of those features. So as a general rule of thumb, as the feature set of a piece of software increases, the complexity is also going to go up, and that complexity incurs extra overhead. So when we're designing new gRPC features, in addition to minimizing the overhead of that particular feature, we also design it such that users who don't use the feature won't incur that extra overhead at all in the first place. Secondly, the gRPC library is long-lived and evolving over time. So as maintainers, we take a more long-term view over the library as a whole when we design features, especially for features that take a longer timeline to implement or are more complex to roll out safely to our wide user base. So to set up a foundation for ourselves, sometimes we make a short-term performance trade-off so that we can invest into fully implementing and rolling out a feature, and so we can reap its full benefits. And a lot of the times, one of those benefits comes in the form of net performance improvements. And we'll talk more about this later. AJ is going to share some examples of some of the performance work that we've been doing and what y'all can look forward to in upcoming releases. And finally, when we evaluate performance, we prefer to look at what's happening to a real production workload, as opposed to trying to tune for a particular benchmark, which could be artificial and not really reflecting what's happening in the real world. So that being said, there's still some amount of benefit to running some form of benchmark, kind of like the benefits of running a unit test, which while it's not going to be able to exercise the complexities of your whole system, it will still give you a useful signal as to whether its behavior has changed significantly in response to like a new change. So internally, we run a set of benchmarks continuously that test various metrics of the gRPC libraries under a variety of scenarios. So we measure things like the latency and throughput of different types of RPCs, and we also look at the CPU load on the clients and servers as they process RPCs. And we test a wide variety of conditions. We vary things like the payload size in our tests. We vary the number of cores on the clients and servers and see what happens. And of course, we do all of this testing in every language that we support in gRPC. So what you're looking at here is a dashboard of our benchmark results, which I'll talk more about in a later section and also share a link. So where does all of this benchmarking data that you see come from? So we have built a dedicated framework which we use to continuously benchmark the gRPC clients and servers by sending RPC traffic between them and taking measurements of that. So we built a lot of infrastructure to help us in our goal to deliver lots of powerful new features for gRPC while keeping the overall overhead low, which is just like the same goal that you have for your services and your applications. You want to deliver lots of cool features, but without a corresponding blow up in the overhead. So let's dive more into our infrastructure and how all of that works. So our gRPC benchmark framework consists of two main components. We have multiple QPS worker processes, and we also have a driver. The QPS workers are what's responsible for sending RPC traffic among each other to form the main workload that we're trying to measure in our benchmark. And the driver is responsible for orchestrating that traffic according to the particular benchmark test we're interested in running. So let's walk through an example. So if we want to run a gRPC benchmark, the first thing we do is we set up all of our workers and we set up our driver. So to tell our whole system what sort of benchmark we want to run, we create a JSON configuration that contains the benchmark parameters. So in this JSON configuration, I would specify things like what payload size I want to run, any sort of client or server specific configuration, and so on. And it pass all that into the driver. And the driver is going to take that and set up the clients and servers. So it'll set up the server first, according to whatever arguments I specified, and then it'll set up the client workers similarly. And it will take the host and port of all the server workers and pass them to the client so it knows where to send the traffic to. If we want, we can also override the server target so that the client sends traffic to another backend if we so wish. But in any case, once the workers have been set up, the driver will send a signal to the client to start sending RPCs to the server, and the client will do just that. So this traffic that's running between the client and server is the load that we are trying to measure in their benchmark. The number of RPCs that the client sends to the server is configured in terms of a duration of time. So for example, I would tell the client in that JSON configuration to send traffic continuously for, say, 10 seconds or for 1 minute. And I can also configure how many RPCs to send simultaneously. So I can tell the client to send, say, 10 RPCs concurrently at once, and the client will have multiple outstanding RPCs. With each RPC, the client will record data points, like the latency of that particular RPC, what was the final status, what was the CPU load it took to process it, and so on. And the server is also going to record similar data on its end. So once the duration of the benchmark has expired, the driver will send a signal to all the workers to stop sending traffic. And at this point, the workers will report back all those data points that they've been collecting over the lifetime of the benchmark back to the driver. And the driver will collect all that data and compute some useful statistics for us, like what was the QPS. It'll build out a histogram of the latencies and compute a bunch of averages and so on. And then it will publish that data downstream to anywhere that we would like to go and inspect those results later. So it can write to a database or to logs or wherever we want. So far we've looked at an example involving one client and one server, and we can do a lot more stuff with this QPS framework. We can spin up multiple client and server workers and have them all send traffic among each other. We can make each worker multi-threaded, so this would cause each worker to process RPCs in parallel, and so we can see what happens to our performance there. We can have each client open up multiple channels, and there's multiple connections to each server, and have it send RPCs on all of those channels at once. And we can also configure your standard gRPC options on all the workers, like if we want to set any channel arguments or particular channel credentials, if we want the workers to be synchronous or asynchronous, and so on. So as maintainers, we want to make sure that we cover all of those possible different scenarios when we monitor our gRPC libraries. So what we've done is we've written a set of tools that will generate all of those various benchmark scenarios for us and pass them over to a test runner, which will run these benchmarks continuously on a dedicated GKE cluster, and it will collect all that data and publish it to the dashboard, which I've linked on this slide. So if you're interested in running a set of gRPC benchmarks for yourself, you can check out the gRPC/testinfo repo, where we've open sourced all of these tools that we use for our continuous benchmark setup. And you can set up your own Kubernetes cluster and run a set of gRPC benchmarks on your own. And this is helpful if you want to experiment with, say, different versions of gRPC or different configurations and understand how that might impact the performance of your application, or if you just want to understand the role of gRPC in the overall performance profile of your particular service. And so now I'll hand it over to AJ, who will talk more about some of the other tests we have and also our upcoming features. Take it away.
All right. Thank you, Ashley. So that was a whirlwind tour of our end-to-end benchmarking system. It's a very important tool that helps us ensure gRPC remains performant under many situations. We also maintain a small army of other approaches to performance measurement and testing in general. In this next section, I've handpicked some other significant pieces of code and infrastructure in our core repository to give you a feel for other ways we examine and exercise gRPC. At Google, we use gRPC pretty heavily, just like you do. And as Ashley said, we understand that gRPC is critical infrastructure, so we aim to tackle performance and correctness from as many perspectives as we can. We're running a little short on time. I might have to fly through some slides. Apologies. Feel free to ask questions at the end. All right. To begin with, measuring performance is great, but the numbers aren't very useful if you are oblivious to them. This is a fantastic dashboard in my opinion, but gRPC developers spend a good amount of time working on things that shouldn't affect performance. And we don't all check performance dashboards every day. So we need something to help us monitor performance and alert us when regressions occur. Luckily, we have a continuous profiling system that runs across Google's fleet of machines, and we get alerted for abnormal resource utilization from binaries that use gRPC. Sometimes a jump in resource utilization may be a good thing, indicating some new gRPC usage. Other times it could be because I wrote some code that added a few bytes of memory to every call, and a few bytes per call can be a significant increase at scale. When regressions do occur, we have a few tools that can help us figure out what changed. One powerful combination you can use is Linux perf and pprof. Linux perf is a standard open source tool available on most distros that collects and analyzes various run profile telemetry like CPU and memory usage. pprof is another open source tool that helps summarize and display perf reports. I particularly appreciate the flame graphs of time spent in each function and system call. You probably can't read it from there, but Here we identified that for this thread pool benchmark, for this one thread, nearly all of the execution time was spent waiting on various lock acquisitions. Finding ways to minimize that lock contention could speed up our thread pool execution if it ever becomes a bottleneck. This graph was generated on demand using open source tools on my development machine. It's a great snapshot of a benchmark, but being able to compare performance samples before and after a regression is invaluable. So running this snapshot regularly is an important part of our process. Moving on, microbenchmarks are intended to exercise smaller pieces of functionality a huge number of times. By focusing on something small and fast and cranking up the iteration count, we can see more than whether or not something is performant. We can quickly see if it is consistently performant. For example, we can ask questions like, do benchmark results vary wildly between iterations, or are they fairly stable? Does performance change as the benchmark progresses, maybe indicating some kind of warm-up factor? Or are the results maybe normally distributed, or maybe something with a heavy tail? Looking at performance at this smaller scale allows us to home in on hotspots, and we use microbenchmarks across the stack. What's shown here is just a sampling of the things we look at. There are over 100 microbenchmarks in the C++ core library, and many more in other implementations. This is one of our actual benchmarks, written using Google's open source benchmark framework, aptly named Benchmark. This code measures how quickly C++ alarms can fire. Let me walk you through this example quickly. The functionality we're benchmarking is entirely inside this for loop, which simply sets a 0 duration timeout on an alarm and pulls the completion queue until that alarm has fired and pushed its tag back onto the queue. The way it works is the benchmark system provides an iterable state object that controls the benchmark, allowing the benchmark system to determine the iteration count and benchmark timing. With command line flags, you can control some of the iteration count, benchmark timing, and things of that nature. Now, this is a fairly trivial thing to benchmark, but we benchmark this because historically this has been a highly performant operation. Quick show of hands, who is familiar with Hiram's Law? Okay, we have 4. Sweet, you're going to learn something. So Hiram's Law states that given enough users, regardless of whether something is part of your API or not, all observable behaviors will be depended on by somebody. And the speed of this API has become very important to a few folks. So while we don't make any claims or guarantees that this special case will remain performant, we do measure it and we do our best. Here is that benchmark's current performance using a simple configuration on my development machine. I'm going to skip the rest of this slide. It's very fast. Okay, let's switch gears and talk a bit about testing. I will skip past the obvious coverage we have for our tens of thousands of unit tests and other end-to-end tests and things of that nature. Instead, let's skip to something more interesting, fuzzing. For a brief introduction for those who are unfamiliar, it's a technique that feeds randomish, hand-wavy randomish inputs to your code and lets you assert that the resulting state is as you'd expect it to be. And you may be surprised to find out that fuzzing has actually improved gRPC's performance as well. Generally, to fuzz your code, you write a fairly small function that takes interesting inputs for whatever inputs may be interesting to your application, and that function then exercises your code. Altogether, this is the system under test. Your fuzzing engine of choice will then repeatedly create and feed new input to your system under test. Coverage-guided fuzzing is a technique where the engine looks at code coverage from the runs of previous input to make informed decisions on how to best mutate the previous inputs so that the code gets exercised in new ways. The idea here is that broadening that coverage is a good way to find problems in your code. Finally, structure-aware or grammar-aware fuzzing improves the fuzzer's ability to increase coverage by guiding the input mutation process. Essentially, custom mutators are used to ensure that the inputs generated by the fuzzing engine are more meaningful to the application. With gRPC, we usually create protos for each system under test that describe the inputs we want our fuzzer instrumented code to receive. This here is a tiny snippet of one very large fuzzer input definition for our API fuzzer. For an example of how this works, the fuzzing engine can provide any input that creates and closes channels and servers repeatedly in any order. The system under test is responsible for taking that input, performing the relevant actions wherever meaningful, and asserting things that should be true are indeed true based on that input. Depending on what sort of coverage was achieved, our libprotobuf mutator then helps mutate the input proto values and feeds that input back to the system for the next run. We currently have over 20 different fuzzers running every single day for a large slice of time on a bunch of machines. Because of them, we have found and fixed security vulnerabilities like the CVE listed here. We found and fixed interesting performance issues, most recently being how DNS resolvers behave when you feed them 64,000 service records. The answer is not great. But we also identified an essential process that could be made lighter weight. And we have many large corpora of inputs that had all caused problems in different ways, all of which are now fixed. These inputs are all now tested regularly for regressions, and they are used to inform mutations for the engine. Finally, I'd like to wrap up with a quick sneak preview of some of the performance-oriented projects that we've been working on for the last couple of years. First, in gRPC Go, the HTTP2 transport framer library is currently being rewritten. The new framer API is based on the idea that we can eliminate most internal buffering and only implement the subset of HTTP2 that gRPC uses. We're also taking an opportunity to eliminate 1 or 2 allocations and buffer copies for every RPC, which could result in a significant speedup. The gRPC C++ library now has a way for applications to take full control of how gRPC does asynchronous execution under the hood, and control how all low-level I/O is done. This is called the event engine. It's a pluggable interface that integrators can use to fully define those behaviors and adapt them to their environments. Right? With this new callback native asynchronous execution system, we can move away from completion queues internally, and as a result, we have a necessary component for a faster public callback API. Finally, gRPC C++ is also undergoing an internal refactoring to a promise-based filter stack. It is heavily inspired by Rust's async model. It's also a template-heavy refactoring, so it lets us make fewer indirect calls, resulting in more efficient code execution. It brings significant decrease in memory usage for every RPC, and it eliminates the need for a handful of mutex locks we have today. Early performance results are very promising, but the numbers are a bit too fresh to share at the moment, and we can expect to reap the rewards later this year. So to sum it up, these are big areas of investment for us. We hope this talk gave you a bit of insight into what we do and a bit more confidence in choosing gRPC for your stack. That's all for us. Thank you for your time, and please let me know if there's any questions. One second. Microphone coming.
Are the data you showed on the slide available for us to review?
Yeah. We have a link to the dashboard, sorry.
Yeah, go ahead.
It's on, here, let's see. Okay, there. Up in the top left, I hope you can see that, bit.ly/gRPCconf 2024 benchmark dash. So this dashboard is available online publicly for anyone in or out of Google to view. And so this just contains like data from all the continuous runs of our the gRPC benchmark framework that we built specifically for measuring like these statistics of the gRPC libraries. So you can take a look. Yeah, I hope that link works. If not, there's another slide where I've included like the direct URL to that dashboard.
If you search the grpc.io blog as well, there are going to be links there and a bit of documentation on how this was created. All right. I suppose that's all. Thank you all.